So in this lesson, we're going to be working with equilibrium expressions again, but this time we're not going to start out in equilibrium. Instead, you're going to start off with a certain amount of reactant or product, and you're going to actually have to calculate the concentrations of those reactants and products once they reach equilibrium. And so in order to do that, I'm going to just provide you with an example and explain as I go. So here you've got a reaction, hydrogen gas reacting with iodine to produce hydroiodic acid. And so here it tells me that my initial number of moles of hydrogen gas are 5.00 times 10 to the negative third, and of iodine is 1.00 times 10 to the negative second. And I'm in a 5-liter container, so I can very easily calculate the concentration for these two reactants. And so because I'm not given a concentration of hydroiodic acid, I'm going to assume that I don't have any. So I'm going to create what's called an ice chart. Now, an ice chart is used when you're not at equilibrium and you need to see the changes that must be made in order to reach equilibrium. So this is an ice chart, just ICE. I stands for initial. So my initial concentration of hydrogen gas is 1.00 times 10 to the negative third. And my initial concentration of iodine is 2.00 times 10 to the negative third. And then that of hydroiodic acid is 0. Now, I'm going to write how those concentrations change. So in order for this reaction to reach equilibrium, I must lose hydrogen gas and iodine, and I must gain hydroiodic acid. And we calculate those changes based on their stoichiometry. So the change that's going to occur, I'm going to label as X. So hydrogen gas is going to lose X. Iodine is going to lose X as well, and then hydroiodic acid is going to gain, but instead of just gaining X, it's going to gain 2X because it has that coefficient. And so now what I can do is I can calculate their equilibrium concentrations. Well, I don't know X yet, but here's the cool thing. This problem actually tells me that my equilibrium concentration of HI is 1.87 times 10 to the negative third. So with that information, since 0 plus 2x has to equal 1.87 times 10 to the negative third, I can actually solve for x by dividing by 2. And so I get x equals 9.35 times 10 to the negative fourth. So to complete this table now, to find my equilibrium concentrations, for example, for iodine, I would take 2.00 times 10 to the negative third and subtract it by 9.35 times 10 to the negative fourth. To get 1.07 times 10 to the negative third. And then for hydrogen gas, same thing, you're going to subtract. And you end up getting 6.5 times 10 to the negative fifth. So these are your equilibrium concentrations, not what you started with. And so using these equilibrium concentrations, I can now calculate my Kc. So remember, Kc is going to be equal to my concentration of HI squared divided by my concentration of H2 times my concentration of I2. And so I'm just going to plug in these values. I'm going to put the 1.87 times 10 to the negative third squared up top, and then the 6.5 times 10 to the negative fifth times the 1.07 times 10 to the negative third on bottom. And so what I end up calculating for my Kc is 50.3. So for these problems that we're going to be looking at in the lesson, keep in mind it's still the same concepts. The only added thing is the fact that we do not begin at equilibrium, and therefore you have to create an ice chart. We'll be creating ice charts for a bunch of other problems, but you use an ice chart specifically when you are not at equilibrium, but you are going to get into equilibrium.
So when we're calculating the concentration at equilibrium, sometimes the math can get pretty tricky and force us to use the quadratic formula, which would require quite a bit of time. So instead there's a cheat called the rule of 100, which keeps you from having to use the quadratic formula in specific instances. And most of the cases that you'll ever see on the AP, you can use this rule, which makes mathematically your life a lot easier. So to start off with, I'm given this equilibrium, and I'm told that I start off with 2 moles of NaCl, and it's placed in a 2-liter flask. And so I'm going to rewrite my reaction, and I'm going to write my ice chart. And I know that my initial concentration of NaCl is going to be 1 molar, and then the 2 other concentrations of products are going to be 0, because I don't start off with any of them. So that tells me that I'm going to lose NaCl in order to create NO and Cl2. So I'm going to subtract 2x because there's a coefficient in front of NOCl. And then I'm going to add 2x and add x. And so what I end up getting for my equilibrium concentrations are 1 minus 2x, 2x, and x. All right, so I'm going to set this up because ultimately what I'm calculating, I need to calculate x because I'm given my equilibrium constant, but let's actually set it up. So using the equilibrium expression, products over reactants, what I need to do is I need to take my x from chlorine and multiply it by the 2x from nitrogen monoxide, but it's going to be 2x squared because there's a 2 coefficient. So instead of being 2x, it's going to be 4x squared. So that's one of the biggest mistakes that people make is they forget about the coefficient. So it's going to be 4x squared times x, which is 4x cubed. And I'm going to divide that by 1 minus 2x, and that needs to be squared. And that's going to be equal to my equilibrium constant, which is 1.6 times 10 to the negative fifth. Now here is where the rule of 100 comes in. If you look at this, in order to solve for x, you would need to FOIL 1 minus 2x squared. You need to get that out of that format. And then you'd end up with an x cubed, an x squared, an x, and a value with no variable. So you would actually end up having to use your quadratic formula or some other form, some other technique in order to solve for x, which is pretty difficult. Where the rule of 100 comes in is that if your concentration that you start with, so in this case 1 molar, divided by your equilibrium constant is greater than 100, if you subtract or add by your variable, you can simply eliminate that variable. So here, 1 divided by my equilibrium constant, which is 1.6 times 10 to the negative fifth, that's going to be a lot bigger than 100. And so what I can actually do is take that 2x, which I'm subtracting 1 by, and just get rid of it. And so now I just have 4x cubed over 1, because it's 1 squared, equals 1.6 times 10 to the negative fifth. That makes my life a lot easier, because now all I have to do is divide both sides by 4, and take the cube root in order to solve for x. And so x ends up being 0.0016. So make sure you check the rule of 100 before you simply just get rid of a variable like that. However, for the most part in the problems we'll be doing, you can eliminate it. So that's my x, and what the question is asking is for me to calculate the equilibrium concentrations for all of them. So what I need to do to calculate the concentration of nitrogen monoxide is simply take my x and multiply it by 2. And so I get 0.0032 molar. For my chlorine, it's just going to be the 0.0016. And then for NOCl, I'm going to take 1 subtracted by 0.0032, and that gives me 0.968 molar. And I've solved the problem. So rule of 100 is not meant to make your life more difficult. It's actually meant to make your life a lot easier. Because if your K, if it's so small that the concentration divided by your K is greater than 100, then eliminating that variable will not have a significant impact on your final answer.